Alright, let's continue our discussion of probability by looking at unions and intersections of events. The formula that we have right here says that the probability of the union of two events, A and B, is going to be given by the probability of A plus the probability of B minus the probability of the intersection. This should look kind of familiar because when we looked at the size of sets, we saw that the size of A union B was going to equal the size of A plus the size of B minus the size of A intersect B. And that's exactly why we have the formula that we do for probability. Probability is just the size of a certain set out of the size of the sample space. And so the probabilities are going to follow the same thing. Here's the key thing that you need to keep in mind when it comes to unions and intersections. If we ever are doing something that's referring to or, so if we have one event or the other, then that's a union. If we have something that is an and, so we need two events to be true at the same time, that's an intersection. So those are your key words. If you see an or, you should be thinking union. If you see and, you should be thinking intersection. Notice that this equation could be used for either the union or the intersection, and we will use it interchangeably for those two things. So let's look at our first example here. We have an inspection of desks at a furniture plant reveals that 2% of the desks have structural defects, 3% have defects in the paint, and 1% have both defects. So this means that we have both a structural and a paint defect. A desk is selected at random. Find the probability the desk has a structural or a paint defect. This should say paint, not pain. The desk is not in pain. Alright, so let's figure out first off what we're trying to find. We're interested in a structural or a paint defect. So we're looking for the probability of a structural or, and the or is the union, so or a paint defect. So that means if we follow our formula, we need to figure out what's the probability of having just a structural defect or having a structural defect. That could include something that has both structural and the paint. Plus we need the probability of having a paint defect, and we're going to subtract the probability of having both structural and, let's go ahead and write it with the intersection. So structural and paint. Okay. Well, let's see. In the problem, we're given some information. 2% of the desks have structural defects. Well, that means then that the probability of having a structural defect is given by that 2%. So if we write this as a decimal, this would be 0.02. So 2% of the desks have structural defects. Let's see. We see that 3% have defects in the paint. So we can interpret this as the probability for the paint. So this will be plus 0.03. If we convert 3% to a decimal, we get 0.03. And finally, we have that 1% have both defects. And so let's see, this will become plus 0.01, again converting to a decimal. And so let's see, the probability that we have a structural or a paint defect is going to be 0.02 plus 0.03. Oh, and I wrote plus, but this really should be minus because we've potentially double counted. By counting the desks that have structural defects, some of those could have also had paint defects, and so that's why we need to subtract that 0.01. We're taking care of the double counting. So 0.02 plus 0.03 minus 0.01 should give us 0.04. And that would be our final answer. The probability that a desk will have a structural or a paint defect. So basically any kind of defect would be about 4%.